All right, today's problem is kind of interesting here. We're going to mix a little fluid mechanics into our projectile motion. So imagine you bought a new sprinkler. You can adjust the angle of the sprinkler, but it also comes on a tripod, or rather an adjustable tripod. You can adjust the height so that you want to sprinkle out this water at as great an area is covered as possible. Kind of makes sense. So covering the total amount of area amounts to some sort of pi times r squared. So really, if I want to maximize the area that's covered by the sprinkler on the grass, I want to maximize the range, the projectile range of the droplets that are coming out of this sprinkler. Okay, now normally this wouldn't be too bad. We've got some speed at which they're ejected from the sprinkler, and we'll have some angle here. The initial height at which the droplets are coming out is something you can control, and then we can calculate r. In fact, previously, we've actually worked out what the range of a projectile launched from a cliff is. It looks a lot like the flat or level ground range, except instead of a cosine theta times a 2 sine theta, we have a sine theta plus this weird square rooty bit, where I've gone ahead and defined this term beta to be 2gh over v naught squared. Notice if h equals 0, beta is 0, square root of sine squared is sine plus sine is 2 sine, and 2 sine cosine is sine 2 theta. So that does recover our original version, but I didn't want to derive all of that from scratch. Let's also assume, just for kicks, that we're fixing this angle theta at 45 degrees. We're really interested in how high should I make the tripod to water the most possible area. Now, kind of obviously, making beta bigger will make r bigger, so you should put it as high as humanly possible, right? Normally, yes. But we have something extra that's coming from fluid mechanics in this problem. And that tells us that if we use the Bernoulli equation for the relationship between the velocity, pressure, and height of a column of fluid that's moving through, say, a piping system, what we'll have is that the kinetic pressure, or kinetic head is sometimes called, 1/2 rho times its speed. And I'm specifically looking at the velocity as it's ejected from the end of the sprinkler, plus rho g times that height. So that's basically the potential energy of the fluid inside of my pipe as it's moving up. This should all equal the gauge pressure in the pipe. Now, you could write this out as like a full Bernoulli's problem where you've got a P1 plus blah, blah, blah equals P2 plus blah, blah, blah. That's fine. But here, what I'm assuming, the assumption that's built into this, is that the gauge pressure in the pipe is fixed. In other words, I don't care if I make this higher or lower, the pressure being supplied to my hose is some fixed value that depends on where my faucet is or the elevation of the water tower nearby, something like that. So P here is the pressure, it's fixed. Notice that these two are rho, not P. I used one stroke to make this rho. I used 2 strokes for the P. And this tells me that if this is fixed, as I raise the tripod, V will go down. And as I decrease the height of the tripod, V will go up. That makes sense, right? If I have a hose and I have it coming off of a balcony or something, the pressure is going to be, or I should say the kinetic pressure is going to be a lot lower. A lot of this pressure head has been depleted just to get it up to a higher level, and there's a little left to make that speed very high. So this throws a little wrinkle into our previous argument. Yes, it would be nice if h were as high as possible, but making h higher also makes v naught smaller because of our pressure relation. Okay, so let's see how we might work this out. I'm going to write down what v naught squared is in terms of h and p by solving for it. Okay, so I'll subtract this over, and then I'll multiply by 2 and divide by rho. Okay, I'm also going to introduce a new variable. I'll go ahead and pull out the 2g, and I'll call this variable h naught, where h naught has been defined as what? P over rho g. Okay, so this is just some other constant. It's basically turning our pressure, our fixed head, into, well, this is actually where the word head comes from in terms of talking about pressure here. It's basically a height that's related to that pressure. Now we're ready to take this expression for V naught. Actually, I could have left it as V naught squared over G, since that's what's going in here, and sub it in for R. At the same time, I'll go ahead and simplify things by using my theta equals 45 degrees. Okay, so V naught squared over G is just going to be 2 H naught minus H. We've got a cosine of 45 and then a sine of 45. All of those are 1 over root 2. Beta is 2gh over V naught squared. V naught squared has this 2g in it. So that'll be this expression. All right, so it's a little ugly as is. Let's clean it up a little bit. So first off, I'll go ahead and factor out a 2 from here, that root 2 from there, and then combine it with this root 2 to cancel the 2 in the front. Now I'll go ahead and distribute this in to both of these terms. Easy first term. The second term's a little messier. When I bring this in, I'll have H naught minus H quantity squared. You might worry about H and H naught. What is their relative sign? We're going to assume that H naught is larger than H. Otherwise, V naught would be 0 and it would just sort of trickle out. So that's not interesting. So we'll go ahead and assume that's okay. When I multiply it into this one, I'll only pick up one factor of this difference because one of the factors is canceled. Now simplifying the inside, when I expand this out, I'll get an H naught squared. I'll have a minus 2h H naught, but then I also have a plus 2h H naught, so those cancel. I have a plus h squared and then a minus 2h squared, which just leaves this. Now we're ready to maximize with respect to h. Little calculus here. We get a minus 1 on the outside, our usual power law type thing here. Don't forget that the derivative of the inside is going to give us another minus 2h. And the 1/2 I forgot about. Let's just put it up in the numerator. That half and that minus 2 cancel. Now something very interesting happens here. Both of these terms are negative. That already tells us, something weird is going on. But let's go ahead and finish this off. I'll move the, the negative h stuff to the other side. But I really am left with a negative 1. Now I can cross multiply and square. The negative sign will go away. And I will end up with 2h squared. So my h should really be h naught over root 2. That's the h that will maximize this. However, we can see that that's not really the right answer. When I took my square root here, I really should have taken plus or negative the square root. And I actually need to keep the negative sign here because in my original equation over here, I do see that h over this positive number is negative 1. So that tells me that the h that maximizes this, I'll call it h star, is negative h naught over root 2. What are we to make of this? Well, it's telling us that if you want to get the biggest possible area watered at all, I should actually start with this thing underground. Now, at first blush, that seems totally crazy. How could I have my sprinkler be underground and water anything? I get you. Let's just say that we have a hole, some sort of conical well that's dug down here, also at a 45, well, I guess it has to be a little higher than 45 degrees. We could work that out if you wanted. But there has to be some conical hole because the price we pay for raising it in terms of V naught squared, which notice it's quadratic in V naught, is so great that it's actually better to have an underground start that'll give you a huge amount of initial velocity to get out and have a higher overall range watered. Now, of course, we're already kind of changing the parameters of the problem because Are you actually watering more area by doing that? Because now it looks like you had to dig a big hole, and this area no longer has grass in it, perhaps, or maybe it's on a slope, or there's some other issues going on at that point. Also, sure, a cone, but what is the actual angle? It's not actually 45 degrees, because we know that if it was, immediately the water would hit the sides of the wall. So this actually has to be shallower than 45 degrees, which means that maybe we're cutting into this this annulus of where we're watering our grass even more. So maybe I'll leave it as a homework exercise to work out, under some appropriate assumptions, how much actual grass gets watered, assuming only the horizontal bit has grass growing on it. Although, of course, if you want to change that and say the slanted area also has grass growing on it, and that the sprinkler is watering everything less than or equal to that maximal range, maybe then your answer here might be a little different. Or maybe we should change our angle theta. Okay, so there we have it. The tripod location that maximizes the total water area watered, at least under some suitable assumptions, is underground. If you can't do this, if you're thinking, well, I'm not going to dig out any holes, and I'm not concerning myself with any watering that doesn't actually hit the y=0 level where the grass is, then the minimum, or rather the maximal value of your range is achieved when H star is 0, meaning when you launch it from the ground and not have a tripod. So long story short, putting your sprinkler on a tripod is actually a bad idea if you're trying to get it to water a greater area, provided we're using a fixed angle. Maybe I'll make it a second homework problem to figure out, okay, relax some of the assumptions about what this angle is. Is there an optimal angle and an optimal H that is not underground that might give you the maximal water range?